Here we're going to look at a roller coaster situation, and we're going to track the energy changes that would take place in this roller coaster. Now, during the beginning part of the roller coaster, it's being pulled up by a track or a chain or something like that. So that is doing work on the roller coaster, and the work that is being done is equal to the change in energy. So at this point, when the roller coaster got started somewhere down here, assuming it was on the ground, it had zero gravitational potential energy because it had no height. The cable or chain, whatever's pulling the roller coaster up this first hill, is doing work on it, and that work is going to be equal to the gravitational potential energy that the car has at the top here. When the car comes down, that gravitational potential energy is going to get converted into kinetic energy. And because this is a roller coaster and this is modeling real life, as it's traveling down this first hill, as it travels down the entire track, that roller coaster is going to be generating sound, which is a form of energy loss, and it's going to be generating heat because there's friction, and that heat is a form of energy loss in what we call thermal energy. So as it travels down, we have gravitational potential energy that's going to be being converted to kinetic energy. At this point here, it's going to have its maximum velocity compared to these points, and actually throughout the entire roller coaster. And that means it's got its maximum kinetic energy, but this kinetic energy here is going to be less than the gravitational energy, potential energy here, due to that loss of friction or due to that loss of thermal and sound. As it comes back up, we have kinetic energy being converted to gravitational potential energy up here. Gravitational potential energy being converted back to kinetic energy here. Now, even though these are roughly at the same height, it's going to have less kinetic energy here, which means it's going to have less velocity because we're losing, once again, to thermal and sound. It's going to continue. Now at this point, it has kinetic energy. That kinetic energy is going to decrease as it goes through this loop. At this point, all right, it's going to have still has to have kinetic energy because if it has no kinetic energy, it won't make it through, but it's going to have a decrease in kinetic and an increase in gravitational potential because it's increasing in height here. As it comes back down, gravitational potential energy is getting converted back into kinetic, and then as it coasts up here, we have an increase in gravitational potential and a decrease in kinetic. I have starred 3 points that we're going to use. We're going to use this here as our initial. We're going to use this as our middle point, and this is our final as we go through and chart out an LOL for this scenario. As the roller coaster goes from its initial position to its middle position, we see that the roller coaster is going to be starting at the top of the hill and then rolling down to the bottom of the hill. All of the potential energy we're going to be looking at in these scenarios is gravitational, so I went ahead and filled those in already. So as it's at the top of the hill, it's going to have the most gravitational potential energy that it's going to have. So I'm going to just go ahead and fill that in. Because it was being pulled up the hill, in order to make it over that hill, it's going to have some initial kinetic energy. So I'm going to give it some kinetic energy here. Once it reaches the bottom of the hill, we said that gravitational potential energy is being converted into kinetic energy. However, it doesn't reach the ground, so it still has a little bit of height. So it's got a little bit of gravitational potential energy there. And I'm going to draw this with 4 blocks of kinetic energy. So that gives us 5. We started with 6 on the left, which means we have to have about half a block of both thermal and sound that is what we say lost to the surroundings or lost to the environment, because that heat energy is going into the rails, that sound is traveling out throughout the amusement park. In our energy flow here, I wrote that gravitational potential energy is converted into kinetic energy, and we have energy lost to both thermal and sound. As the roller coaster goes from its middle to its final, our description, we have the roller coasters traveling from the bottom of the first hill to the top of the second hill. This is what we're starting with now. We're only going to focus on the gravitational potential energy and the kinetic energy because the thermal and the sound, remember we said, was lost to the surroundings. it's going to be gaining gravitational potential energy, but it's not going to be gaining as much as it had in the initial position. Maybe we'll say that it gains 1 block. So we'll have 2 blocks of gravitational potential, which means we have to have a loss of at least 1 block of kinetic energy, but we've still got energy lost to thermal and sound, so I'm going to have it lose 1.5 blocks, which is going to take us to 2.5 blocks approximately. And then that leaves us, approximately about 1/4 of a block for thermal and 1/4 of a block for sound. And lastly, in our energy flow, we could describe this by saying that kinetic energy is converted to gravitational potential energy, and we have energy that is lost to both thermal and sound. If you wanted to, you could continue this process, label more parts on the roller coaster, and continue to track the energy flows, but I'm going to end it here because I think you've got a pretty good grasp of what is going on. Thanks, and I hope this helps.